Welcome back, students. For today's lecture, we'll look at how data are stored in Android devices, and we'll be using the book that is recommended for this part of the subject, which is you can get the book online from our TP library, or you can get a hard copy book from TP library. So if you actually get the book online from TP library and you're going to download it using the Adobe Digital Edition, this is where you get in the library or in your Adobe Digital Editions. They call it the ADE. And let's look at which chapter we're looking at for today. The previous lecture we covered about chapter 1 and 2, so right now we'll look at chapter 4 then, and we'll be looking at this part over here. It's called how data are stored. So in Android devices, how data are stored, there are 5 methods that are stored: shared preferences, internal storage, external storage, SQLite, and network. So these are the 5 methods that the persistent data, that means permanent data, are stored either in NAND, flash, the SD card, or the network. So these are 5 methods. Let's look at the very first method called the shared preference. In the shared preference, we look at what are shared preference. Shared preference are nothing special. It's just an XML file. XML file is just a normal text file with a lot of data inside. So it's just an XML file with some predefined data types. What can you actually store in this type of data types? For example, like Boolean, true or false, floating point, integer, long integer, and string text file. So let's look at one of the example of this XML file then. Let's look at one of the example of this XML. One of the example of this XML are stored under, for example, data. This is a place where you store all your data files, and under Android phone, and you see 1, 2, 3, 4, 5 type of XML file are there. So let's look at one example of the XML file, which is COM Android phone preference, which is here. You can cut it out at COM Android phone preferences XML, and you can see inside this is the XML file. And of course, you can see things such as the version, the encoding, for example, the CDMA files, numbers, string with asterisk 86. But it is forensic data interesting data they want to have. We can actually look at one file which is called the update area code XML, which is here, update under here. So inside this file there's something called MDN string. So inside this MDN stands for mobile directory number. So what it does is that every time if your mobile phone query a MDN, you will record the area code for this phone. So what happens is that let's say you are in some state in some area, and you want to query, the phone is querying a MDN, it will store this number like 312 belongs to a certain area of this country. So what happens is that if you view this file, update area code.xml, if you look at this string, you will give you the latest mobile directory number or the area code that this phone is. It won't give you the history, but it will give you the latest. So give you some understanding of where does the phone has been. The next one we look at is file on the storage, or they call it the files on the internal storage. So the file in the internal storage can be in the, mostly it's in the NAND flash. So these are called the internal storage. Most of the time the file are stored under this directory called data. That means your subdirectory under this data directory, and this is where all the application developers or application are stored under this directory. For example, your contacts, your Facebook, your Twitter, whatever application, mostly are stored over here. If you look at this itself, let's look at one example. If you look at Google Maps, so for example, Google Maps is stored under this directory called data and com, Google, Android apps and maps. So inside these directories, you can see the whole lot, all the directories of the data are stored there. Of course, in particular, we can see the store preference, shared preference, sorry. This is one we are talking about just now. If it's some data, it might be interesting forensically or might not be. If you look at the tree map, you can see the number of data are stored there. So these are the trees, the files are stored by Google Maps. And based on this, it will give you some ideas that where does what type of maps has been used by this phone while using for Google Maps. So this is one of the internal storage. The third storage data, how data are stored in Android, will be files on external storage. So what do you mean by external storage? In Android devices, external storage will be like removable SD card. That means since NAND flash are pretty expensive, or internal storage, so majority of the high so-called huge capacity type of media files or files are stored in SD card or removable SD card. Mostly is mounted at this directory called /mnt or mount SD card. So this one will be your mounted directory. And if you look at this, you also can see some of the data Android store for the cache of their maps over here. Of course, you get some other data can be stored for media, also can store over here. For example, if you take a photo, if you store the photos that you have taken inside the SD card, it will be stored somewhere or other inside the MMT, for example, MMT SD card, and then your photos. The fourth place where the data can be stored in the Android device will be under SQLite. Yes, we have been discussing about SQLite in the last 2 lectures. So SQLite will be the database, is where the developer can store specified file called SQLite in database. So this is quite easy. So-called we have been discussing about this. So this one method is store the data. The last method that they would store data is under network. That means that when applications access a network, whether it's using the JavaNet or you can use an Android application to go through it. And mostly when you do this type of network accessing, you will tend to write some of the data in the log file. It gives you some idea of how the network is being accessed, or sometimes they pass information through a network where you can have some forensically interesting data where you can pull the data out. Just give you an example called Dropbox. So this one example called Dropbox. So inside this Dropbox itself, you can see that there's a database, there's a log file, there's some shared preference. So this is some of the things that we talk about there. So inside the log file, we can see that this log file is pretty, there's a lot of information inside. What we forensically interesting inside this log file is that, all the log file data are timestamped. That means you have a timestamp. You can check the time that is being accessed or being how the information or the function is being used. The other thing is that we can see that username are exposed. That means that we will know who used the Dropbox. For example, book via forensic.com using this. So this is some of the information you can get from the Dropbox if you're from the log file. The other thing we can see, if you look at the shared preference, we can also see that the names, there is the name for this Dropbox Of course, you can see things such as reference link. Of course, you won't see password over here. You can see the email addresses if you want to know the email address of this Dropbox. So this interesting data use another example for your shared preference. The database SQLite, you can see if you manage to query it, you'll see data such as what our file has been added to the Dropbox. So these are some data you can see over there. So we have finished looking at how data are stored in Android devices. Welcome back, student. Today's lesson we have covered type of memories and where do we get the materials from. You still remember we get from this book, Android Forensics, and the soft copy of the book again can be downloaded from TP library with the 7 days renewal, and if you want to borrow the hard copies of the book, you can get it from the TP library. Let's start now. Today's lesson we will cover topics from chapter 4 and under the subtopic called type of memories. And today we will look at the type of memories in the Android, which covers two parts: the volatile memory, which is the RAM, and the non-volatile memory, which is the NAND flash or RAM. Apparently, RAM is the same as normal computers or laptops, where it's used by the system to load, execute, or manipulate operating system, application, or data. And of course, like most traditional computers, RAMs are volatile. It means then, what do you mean by volatile? It means that when the Android device are powered off, the data in the RAMs will be gone. So what are the examples of the RAM data which is useful for today's in terms of the Android forensics? What can be stored in the RAMs? Examples are password, encrypted keys, usernames, application data, and system processes. So if you can pull the data out, that means that if you can pull the RAM data out from the Android, you might able to get some of the data in the RAM. But bear in mind, there's two types of RAM data we are talking about here. One type of RAM data is for the RAM of the whole Android operating system. That means that, let's say the RAM of this Android device is 8 gig. If you actually pull the Android RAM data, is 8 gig. Irregardless of which applications is using the RAM, you get 8 gig of them. This is the ultimate best method to pull the RAM, which is very difficult to do it in Android. So the other way is called the application app memory. That means that you get the application process ID, and you get the memory of that application. Question? Yeah, the students ask, he don't get a difference. Okay, let me repeat again. There's two types of memory you're talking about here in the RAM. One is called the Android memory. If you have 8 gig of Android memory, you have 8 gig of them. Application memory means that, for example, you have Twitter or a Facebook application, you are given, for example, only 500 meg out of the 8 gig. So, for example, Facebook will have 500 meg of memory, Twitter will be 500 meg, and so on. So if you only get the application memory, that is only, for example, 500 meg. It doesn't get the whole Android memory. So in this book, it covers some of the methods. Also in the labs also, we cover some of the methods that you can get the memory dump from the application. So it's an application memory. Might not be for example, you get a memory dump from the Facebook, and you can look at the data of the RAM in the Facebook apps. Let me repeat again. If you go by this way, it's called the application apps memory. not the whole Android memory. So this one method. What can you get from the app's memory? Well, you can get maybe the username, a password. That depends. So you can try out in the labs. Also in the case study, you are asked to look for the app's memory. So this is the first one, the volatile memory. As for the second one, which is the NAND flash, which is considered the non-volatile, that means that when the data is powered off, or sorry, when the Android is powered off, you are allowed, or the data will be safe and will not be lost when the power off of the Android device. This NAND data has a different characteristic as compared to magnetic disk. First, there's no mechanical part. So this flash data has no mechanical part as compared to the traditional mechanical hard disk. This improves the durability and the size and the power consumption. Improve the durability means that it will last longer as compared to your mechanical hard disk. Reduce the size and the power consumption means due to there's no mechanical hardware inside. There's only NAND chips for your flash device. That means you can consume lesser power and lesser in size. So NAND flash is high density, means that you can create a lot of them. Cost effective to manufacture. Okay, bear in mind, if you look at the market or you go Sim Square, you realize the cost of an SSD or NAND flash hard drive is still very much expensive compared to the traditional hard disk. So what do you mean by cost effective here? It's trying to say that there's a lot of way to make flash device. You can have the NAND way, the N way. So NAND flash, the way to create the flash is much more cheaper as compared to the other method of creating a flash device. It doesn't mean that this is cost effective against or compare with traditional mechanical hard drive. It's still expensive if you look at the price of today's SSD flash device as compared to the hard disk. Okay, what is the disadvantage then of a NAND drive, since you have so many advantages? So the disadvantage is that the NAND drive tend to have a lot of black or so-called black block due to the manufacturing. So what happens is that there must be a lot of way so-called for the NAND device to track the black block and remove them from the system. That means that during the manufacturing of these NAND flash chips or device, it tends to create a lot of bad blocks or faulty blocks, so that in such a way that you need to have some way of tracking them, all these black block, and remove them operation. The other limitation for a NAND flash is that it has a very limited read-write lifespan as compared to the mechanical hard drive. What do you mean by limited read-write? That means that let's say there's 5 chips here, 1, 2, 3, 4, 5. If you keep repeating writing to one part of the chip in the flash, once after a while, as compared to the number of writes you have, compared to the number of writes or read-write you can have for the hard drive, this part of the chip, flash device or this chip will be down, and after that you left with only 1, 2, 3, 4 to write the data. So what I'm trying to say is that they tend to do a round robin so that you don't keep writing the same chip on the flash device over and over again. So this is the other limitation. We'll look at what is some definition for NAND drive, NAND flash. There's the lowest, if you still remember, the lowest so-called readable or writable chunk in a normal hard drive or traditional hard drive would be like sectors. But in NAND flash, it's either named as the lowest unit that you can read or write, will be referred as chunk, or sometimes they use the word page. So either you can page or chunk refers to the lowest unit that you can access or read or write. Give you an example. The NAND flash, of course, as per on the normal traditional hard disk, a lot of sector will form a block. So like in Linux, so a lot of chunk or page will form a larger uniform. Is called a block. So this I say. So a normal NAND flash block consists of 64 chunks of data, example, and each chunk is 2048 bytes. So in totality, will be 64 times 2K. 2K is because of the 2048 bytes, and the block size will be 128K bytes. So this is how you actually look at the size of the NAND flash drive. The other thing we'll look at is characteristic of NAND flash is that the NAND flash support 3 types of operations. It's called the read, that means to read a page, that means the lowest unit page. To write a page, the lowest page, or sometimes you say a block, sorry, not a block, sometimes you say a chunk. Read a chunk, write a chunk, or read a page, write a page. But to erase, you must erase a whole block. That means a numbers of chunk or page together will form a block. So this is what I'm trying to say. What happens is that the only operation you can do for erase is on the block level. And when a block is erased, the entire block is overwritten with binary 1s or 0xFF in hexadecimal. So what happens is that if you want to erase, you must erase a block. You cannot erase a page. So back, if you have 64 page per block and you want to erase one of the let's say you have 64 page per block and you want to erase page number 4 inside the block, you can't simply just write off page number 4. You have to erase the whole 64 page in the block, because this is how the way it works. So in that case, it means what happens? It means the erase operation is only possible that can change from 0 to 1. Let me repeat again. For a NAND operational, there's a special case for changing a 0 bit to 1 bit. That means that in order to change a 0 bit to 1 bit, that's the only way to change it is using the erase operation. You cannot simply just write to a page. You remember, you can still write to a page. You can write to a page and try to change from 0 to 1. Yeah, it's not possible. You must erase the whole block. How about changing from 1 to 0? Yes, you can change the bit from 1 to 0 by doing a write page. How about one example over here? Maybe you can see the reason. Okay, let's say you want to do an addition of 179. This is to add 179 to 39, give you 218. So what is this example trying to say is that, let's say initially this byte is 179, and you want to a new byte, you can, after you add 179 to 39, you get 218. This is 218. So what I'm trying to say is that, let's say you only have one page per chunk, one page per block. So this one page is only 1 byte. So what happens is that you 179 plus 39 will give you 218, and you're supposed to write this back into the same byte. But due to the operation, if you still remember, the operational is that you can write 1 to 0 or change from bit 1 to 0, but you cannot change from bit 0 to 1. So you say this is 179 and you try to write to 1 to become 218. So 1 change back to 1, no change. This one will be enforced. 0 to 1, well, you're not allowed, remember, so it will goes back to 0. 1 to 0, yes, it's allowed, so it's 0. 1 and 1, no change. 0 and 1, you're going to try to change 1, cannot, so it'll be 0. 0, 0, no change. 1, 1, no change. 1, 0 is allowed, so it'll be 0. So in totality, what happens after you do the NAND write is that you end up with this byte over here, which is 146 rather than 218, because the let me repeat again. in a NAND operation, the only way to change from a bit 0 to 1 is an erase operation, and you must erase the whole block. If you want to write to a page, you can only write the bit 1 and change back to 0. Of course, the other way is to don't change anything. So of course, if you don't change anything, then it might not be necessary to write the whole page itself. So for the NAND flash device, after we do a summary for this this part of the NAND flash, you realize there's two important techniques that is deployed. One is called the error control code, because there's a lot of bad blocks, so they need. The other one is called wear leveling. That means that they try not to use the same chip over and over. So let's look at ECC now, error control code. So this is a technique. It's an algorithm to detect back sectors or back errors or data errors or correct some error on the flies. So what happens is that if there's some, for example, after the number of readings, typically, let's say you try to read or write to the same page or chips for a few times, but it does not, it's not possible to do it. It's considered as a page or a bad block, and you're not supposed to use it there. The second way of preserving the flash, because it's there's a lot of limitation, is that it's called wear leveling code. That means that you try to write the data across the entire flash and do not use the same flash chip over and over again, or same page over and over again. So this is the other limitation you have over here. As we discussed before, because flash devices are raw device, and Android are built in such a way that they deal directly with the flash device, so they must have some layer or software layer that manage the flash, and this layer is called MTD, which stands for Memory Technology Device. And if you still remember, this MTD sound very familiar because we actually discussed this before in the previous lecture under this lecture, and under slide number 12, it says that traditionally most Android device doesn't have the required so-called MTD, or this memory technology device, this layer over here. So it's a software layer you have to implement to access the flash. So this is the part we are talking about here. Of course, you have a flash translation layer over here. So what happens is that this MTD does not only provide a block interface to NAND flash, because if you still remember, Linux, Android is built on Linux, and Linux are block interface device, and also it help provide the ECC or wear leveling device. So in order to provide the ECC or error controlling correction code, is that they must reserve an area inside called the OOB, or out of band. What do you mean by this? Let's look at these little blocks over here. So in this example over here, if this chunk is 2048 bytes or 2K, there will be 64 byte OOB or out of band that store metadata about this chunk over here. For example, you can store whether they are bad block or they are good block, they are the reserve block, they are the they call it the erasable block or stuff like that. So this is called the metadata of the whole chunk over here. So if there are 5 chunks, and there will be 5 OOB. So this part over here is like overhead where you cannot store any data, but yeah, this one must be there for the whole block itself. So this is what this whole slide is about. A little example we can see over here is, of course, this little example will show that this block is 120k bytes and 64 chunk, and every chunk is 2k plus a OOB. Okay, this is what I'm trying to show over here. A little example when you can look at, if you say use this command, if you still remember ADB is the access to the Android device, the shell command, and cat out the file under the proc called MTD. You'll see, for example, MTD 0, the size is this. This is in hexadecimal, and erasable, that means this is a block size for miscellaneous subdirectory. give an example, let's look at the system directory itself. So for the system directory, is over here. This is the size in hexadecimal, the size in bytes in decimal, and the size in kilobytes and megabytes. So it's about 248 megabytes, and it's reflected here, the system, when you show a cat for the proc MTD, and the erasable size will be the block size of the NAND flash, which is 20,000 or 20,000 in hexadecimal. It means that 0x 20,000 or 131,072 bytes, or it's the same as 128 kilobytes. And this one is the same as we discussed over here, which is 64 page, and or they say 64 chunk, and each of them is 2048 bytes. So it's the same. For even though cross-reference it, you can do a DF for the system folder, and you can see the same thing as you repeated over there. In this part, we will look at the file system called YAFSS2, which stands for yet another file system. And we are going to look from the books. This is the same book that we look at, and we look at we're going to chapter number 4, and we look at a subtopic called file system. If you are following the books, please go to page number 141. Let me scroll to 141. So this is the page number we are at, and we're looking at this yet another file system too, YAFSS2. We can look at this file system is going to use on the NAND flash device, and we're going to look at what's so great about this file system. So why YAFSS2 is selected to use for Android operating system for most at least from 2.3 and below. Why are we still covering this? Because for quite a number of Android devices are still on 2.3. Most of the Android 4 are in ext4 file system for the NAND flash device. So back to the YAFSS2. Why are we using YAFSS2 for Android device? There's a couple of the advantage. First of them is a log structure file system. That means that even there's a power failure in your Android device, it's able to recover back, and the file system will be in a consistent state. That means, for example, you are doing something, you're watching YouTube, you're playing some games, or you're updating a context, and suddenly the battery just go flat. It's able to recover back to the previous consistent state before you play game, before you update the context. You also provide built-in wear leveling and error correction, so they call it ECC, that we discussed previously in the lecture, saying that all the NAND flash devices suffering from, if you keep writing the same NAND chips, NAND chip will be so-called spoiled and will be in the back bad sectors, or sorry, back chips. So what happens is that the wear leveling is that they come trying to write the chips or everyone write one times, then when you do a round robin, come back, then write the first chip, second chip, then go back to the first one. Error correction is when there's a bad chips, how do they so-called mark it as bad block, how many times of readings before they consider you is not able to read or write. So this is one of them, capable of handling back blocks that we talked about just now, and it's as fast and small footprint in RAMs. This is important because in most of all the Android devices or mobile phone, RAMs are quite limited as compared to the RAMs inside the normal traditional computers. So the file system must be small enough and fast in the RAM to provide the file system things. You still remember all the NAND flash device has so-called the data chunk followed by OOB, or call it the out of band data. So every chunk has its one OOB. So this is what is the OOB, what is inside the OOB. In the 64-byte OOB or out of band for every chunk of data, it does have the block state, whether it's good or bad. If you see 0xFF, then it's good. If other value is a bad. Of course, there's something like, for example, the sequence number, saying that whether which one is the highest sequence number is the latest block. The older sequence number are considered obsolete block, so it won't read it. But bear in mind, although you see the 1 byte here is block state, the 4 byte here is chunk ID, object ID, but the specification for this YAFS2 doesn't so-called hard code that the first byte must be a block state, the next 4 byte must be some chunk ID, and the next 4 byte must be the object ID. It's up to the implementation of the YAFS2. For example, Galaxy 3, Samsung has a way of implementing it, HTC has a way of implementing it, and Linux has a way of implementing it. So what happens is that this poses a problem when you are doing a so-called extraction of YAFS2 straight into the, for example, commercial tool or automated tools, and because they expect the first byte might be a block state, but it might not end up in that stage. So the whole acquisition or the whole analyzing will fall and will not end up in the correct things then. So that's why the manual is still quite important. Manual way of doing analyzing of the NAND of the file system is still important. The next part here is that we're going to create a NAND or YAFS2 file system from the NAND fresh. It's going to do it in the lab, so you're going to look through it. This part here is installing the MTD utilities. That means that how to do the how to access MTD. You still remember media technology devices. So for the NAND fresh device, you should download the YFS2 source code and you untar it. This part over here, you make it means you compile it in Linux based on your operating system, and you load the module in, the kernel module, load it in, mobprobe, and mobprobe the MDB block. You create the NetSim simulator. Okay, what is a NetSim? NetSim is just because we try to simulate a NAND flash device in the hard disk, because it's either you have a lot of NAND flash device floating in your so-called you can spare to use it, or you can create a simulator, a NAND flash simulator, and try to access it. So this is the way. It's the type NAND probe net simulator, and these 4 arguments over here, 1, 2, 3, 4, will decide what is the size of this NAND flash and what is their chunk and block size. So these are some examples over here. For example, if you use these 4 arguments as first byte is this one, second byte is this one, you produce this thing. And for example, if you use the first byte is this, second byte is this, third is this, fourth is this, you produce 64 megabyte with 2048 page or chunk then. So it depends on which one you want to create respectively. After it's created properly, you can do this command called cat mobprobe, cat the MTD, and you see this, you say, so what's the size? 400,000, okay, 4 million, right, is 65,000 kilobytes, or 65 meg, or 64 meg in terms of this, and the array size is 20,000 is 2048. So with this in mind, you can insert or load your kernel module of this YAFS2 so that you start reading the simulator partition then. If everything goes good, what we're going to do is that we try to use NAND dump. Why we want to do NAND dump is that we want to see the NAND flash device simulator they created, what is the data inside. So you must use this command called NAND dump. Of course, the student so some students might be wondering, Some students might be wondering what's the difference between NAND-dump and the normal hex editor. Well, then if you do a normal hex editor, you not only you might not able to see all the data properly, because the hex editor will actually see everything. That means that the hex editor doesn't know how to so-called read the NAND device properly. That's the reason why we need to use the NAND dump and to dump all the NAND things into the file, and use a hex editor to read it. So in this example, NAND dump will dump everything, everything of this NAND device simulator that we just created. We pipe it to the so-called SSD. SSD is nothing, just a hex editor viewer, and we look at all the data inside. If you look at all the data, it's all the F stand for all the 1. That means it's totally erased. You still remember, if you erase a block, it will be all overwritten with binary 1 or in 0xFF in hexadecimal. And if you want to use a file system, you have to mount it as per normal that you learn in your SADS, to mount the file system into a mount point. And after that, you can start. If you view the mount point, you can see the dot and dot dot is still the root and the previous one, and then lost and found. So what happened right now is that we can add something inside. For example, we do an experiment. You can nano and then write a file called book.txt. This is a file, we create a file, and we put some context called Android forensic and mobile security inside the created file system. If you still remember, this mount point is link or mount on using the NAND simulated NAND flash device. If you do a NAND dump on that same so-called NAND simulated flash device that we created just now, you realize the first block, you see the book name is there. This one is a header, the block header, or they call it the block header. Then you see the content, and you see another block header called book. What happened here is that the first so-called this header, the chunk header, say this is a file name. There will be no content. The file name is file length is 0. Next, they write into the next chunk with the content, and we still remember you are not possible to overwrite the same chunk of data, because the only way to do overwriting or erase is to erase all everything gone. So what happens is that they'll write another chunk header called book.txt. You see the name is there, but in this one it will say that this is the latest one with the proper serial number, higher sequence number than this part here. So this part over here, or chunk header, is considered obsolete. This one will be the current one with the correct file name and reference to this data itself. So this is how it works in this example. In this part, we will give you a example called YAFS example. We will simulate the fictitious file system, and we look at this file system. Initially, we try to create a file here. If you try to create an empty file, what happens is that the block is 0. Remember, the chunk numbers in the block is 0. The object ID is 500. Chunk ID is 0. It's live, means it's good. It's not obsolete, it's live. And this object length for the blank file is length 0. Next, you write 3 chunks of data into the file. And when you write 3 chunks of data, in this example, as I say, this fictitious NAND flash has only 4 chunks per block, or 4 pages per block. So if you write 3 of them, that means that this is still block 0. But right now you write 3 block 1, 2, 3. The ID is still object ID is still 500. The chunk number is 1, 2, 3. They are all live because this first chunk data, second chunk data, third chunk data. But if you still remember, you say, oh, Mr. James, how come this length is still 0? You're right, because that's next part that this file system might have to be updated into this way. Because the file name has changed, file length has changed from 0 to 3, you need to write another chunk. Right now they need to write the 4th chunk, but since there's only 4 chunks per block, you need to write into the next block with a new chunk stating that this is a new object header for 500 with the length of 3. So if you realize there's two 500 header, this one and this one, but what happens is that this is obsolete, this one is the latest one, and in the status for this old obsolete, you'll be highlighted as deleted or shrink, and this one become live, means the new. In summary, this little example gives an idea how the NAND file system work, the YAFSS2 system work, and you realize that it's not possible, or you will, when you write a new thing on new file or new chunk, you will try to write to a new chunk in the same block or different block, and then try to change the status. So that what does it means in terms of forensic is that the old data will be still in the file system, the NAND flash device, until the garbage collection come and erase everything, the block into FF in terms of hexadecimal or 1. So this one of the concept in this YAFSS2 file system. That's the end of this lecture. Catch you in a bit.